Every health AI you've used has a privacy policy. Every one of them says some version of "we will never sell your data." Here's the problem. Cerebral, a mental health app trusted by over 3.1 million patients, shared their data with Meta, Google, and TikTok. Flow Health, used by over 100 million women, shared menstrual cycle data with Facebook and Google. GoodRx was fined $1.5 million dollars by the FTC for sharing prescription data with advertisers. And BetterHelp settled for $7.8 million dollars for sharing therapy data with Facebook and Snapchat. Every single one of these companies had a privacy policy. Every single one of them broke it anyway. That's not a wording problem. That's not a bad actor problem. That's an architecture problem. If sensitive health data is sitting on a server somewhere, someone eventually will find a reason to move it. So we decided to remove this server. This is Sirius. I built it with Erina Karate and Dipan. The three of us are CS grad students at the University of Minnesota in just 24 hours. Sirius is a private AI health companion for iPhone and Mac. And the core claim is very simple. Gemma 4 runs entirely on the device, not mostly on the device, not partially on the device with the fallback to the cloud, entirely on the device. Here is a bit of the shape of the system. On the iPhone and on the Mac, inference happens locally. Voice, camera, text, everything is processed right there. Health memory lives in an encrypted SQLite and it never leaves the device. The two devices can sync directly with each other, peer to peer, no server in between. And the only thing that ever crosses out to the internet is a single, narrow, sanitized web query, stripped of anything personal before it leaves. We'll show you how exactly that stripping also works later. This kind of on device private AI approach is exactly the direction the whole industry is heading now. We built Sirius ahead of that, becoming the obvious mainstream way to do it on Apple hardware when running a real model locally on a phone, which was the harder part, but not the standard one. The privacy guarantee here isn't a promise somebody could quietly walk back in a future policy update. It is the absence of a server to walk it back on. My piece of Sirius was the iOS app, the full Gemma pipeline, and the voice layer. The obvious first move for running a local LLM is llama.cpp. It is battle tested, huge community choice, and the default choice. I tried it. And at that time, it had no support for the model we wanted to run. And we reached sort of a dead end during the hackathon. So I kept exploring and I landed on Google's LiteRT framework. That's the rebuilt on device optimized successor to TensorFlow Lite, which had Swift bindings together known as the Lite RTLM Swift. This gave me a direct path to just load the model's weights and run inference using the iPhone's neural engine and GPU through Metal. Getting it loaded was the easy part. Getting it to stay loaded was the hard part. Even quantized, the model is not a small guest on the iPhone's memory. On older devices, it would just crash because it was taking a bit more RAM and the devices were using a bit older hardware. So I spent a bit of stretch on Apple's memories profiling tools and worked through the quantization configuration until it fits comfortably from an iPhone 13 or above without losing the reliability of tool calling. And here's the thing I want to land on. First token latency on this came in under 200 milliseconds. It's not because we have a fast server. There is no server. There is no round trip to wait on. There is nothing to round trip. Everything happens on device. The voice pipeline follows the same rule. Speech to text runs through Apple's SF speech recognizer with on device recognition forced on. So your voice never touches Apple servers either. The response comes back through the AV speech synthesizer. So you tap, speak, and you get an answer with everything being processed entirely on your phone. Here is what it actually looks like.
What are the side effects of metformin?
Metformin can cause a range of side effects, which can be categorized as common, severe, or long-term. Common side effects. These may include nonspecific symptoms such
I took the Mac side, and the first wall I hit was a platform limitation. You can't call MLX directly from Swift. So what I did was I built a small local Python server using Fast API that bridges the two things, and it only listens on localhost. It is never exposed to the network. It's local only by construction, not by configuration. For the inference engine itself, we chose AppleX's MLX framework over Core ML or GGUF. MLX gets the best performance on Apple Silicon for this model, and at the time, the Swift bindings for MLX were not stable enough to use directly. One quirk worth knowing, this model does not have a native system role. So when we build the prompt, we fake it, injecting it as a user and assistant exchange instead. We also hit a real bug worth mentioning. Running inference and text to speech at the same time caused a metal crash. The fix was a threading lock that serializes the two so they never collide. The other piece that I built was the PDF import. PDFKit extracts text page by page, and if a page is scanned rather than typed, Vision OCR picks up the slack. The whole document gets parsed locally into structured fields, medications, conditions, allergies, etc., and the user reviews and confirms it before any of it gets written onto the health memory. Here's what it looks like in practice.
I spent most of my 24 hours on one question. A local model can answer a question privately, but health isn't one question, right? It's appointments, PDFs, prescriptions, lab results, and wait, what did the doctor actually say? Without memory, the assistant is smart, but it basically has amnesia. It would ask what medications you're on every single time, and we don't want that. So I built the memory module, a standalone Swift package from the app itself that stores, retrieves, summarizes, syncs, and protects personal health context entirely on the device. Here's the design choices that I cared most about. I did not want this to be throw embeddings at the wall and see what cosine similarity thinks about your allergies. No, some data is too important to be retrieved probabilistically. So retrieval is hybrid and structured first. Allergies, active medications, and active conditions are always pulled through a direct SQL query, deterministically every time, regardless of what else is competing for space in that context window. Semantic search using Apple's NLE embedding, 512 dimensional vectors, cosine symmetry, etc., handles the softer stuff like conversations, documents, things where meaning matters more than an exact field. A context assembler then combines both allergies first, then medications, then conditions, then semantic matches, all within a fixed token budget. So, why does this matter so much? Because if a patient is allergic to something, I don't want fact competing with a random paragraph from a PDF because they happen to look similar in the vector space, right? In healthcare, forgetting an allergy isn't a personalization gap, it's a real critical safety problem. And a couple of other things this module does is it separates raw medical records from conversation history. Medications, allergies, lab results, and documents are all protected and never get summarized away. Conversations can be compressed over time, but every summary keeps a link back to the original turns it came from. In testing, that compression hit 80.6% on a verbose conversation, while still preserving the medication names and dosages that actually matter. It also does contradiction detection. If a new dosage disagrees with what's already on file, the system flags it immediately and keeps both versions rather than silently overwriting. In medicine, you don't want to auto-resolve that. A person usually would instead. So all of this runs on top of a 16-table encrypted schema with a single external dependency and 121 tests passing with zero failures so far. And I'll be straight to you. This is kind of a hackathon grade verification, not clinical validation, but it made the system feel real and it's a foundation, not a finished product. So yeah, this is what that retrieval pipeline looks like with something real instead of a typed question. Point the camera at a label or a lab report. On-device OCR through Apple's Vision Kit pulls out the text, so no upload, no cloud OCR service touched at any point. Those values get matched against what's already sitting in memory. Now watch this. The answer that comes back references both the scan and the medications already on file. Nobody had to retell it anything.
Now, memory isn't just reactive, it's also proactive. Sirius reads your calendar on device through Apple's event kit and notices when a health related appointment is coming up, a GP visit, a cardiology checkup, or anything flagged by keyword. The day before, it surfaces a prep brief. And that brief isn't generic, it's built from your actual health memory. Your current medications, your recent labs, what have you been asking about lately? It tells you what to bring and what to ask.
So far, everything I've talked about stays on the device, but sometimes the model genuinely needs something it doesn't know, like a recent FDA warning, an updated drug interaction examples. For that, Sirius can search the web. And that's the one place in this whole system where something leaves a device. So it has to be the most carefully guarded part. The memory module treats the web as an untrusted boundary, full stop. The web agent never sees the user's personal health record. It only ever sees a sanitized query. Here's what that pipeline does step by step. A redactor strips direct identifiers and personal health markers before anything is sent out, including social security numbers, dates of births, phone numbers, emails, personal dosages like 500 milligrams, etc., temporal appointment markers, possessive health language like my diabetes, and any person's name caught by Apple's NLP name detection. What it keeps is the generic medical terms because metoprolol side effects, I can't even say it, is a useful question, and it is not the same as sending someone's identity and appointment history out to the internet. Every one of those redacted queries gets written to a local audit log before it goes anywhere. Then and only then does the sanitized version go out, and only to a fixed whitelisted, trusted medical sources like the FDA, NIH, CDC, Mayo Clinic, PubMed, and a handful of others. If we had this on stage live, this is the exact moment we'd open a network inspector and show you the actual outbound request, and you'd see a clean medical question and nothing personal in it. So that was our proof for that. But one more thing this boundary protects against going the other direction. Anything a user uploads, a PDF, a scanned label, OCR text gets treated as data. not as instructions. We sanitize for prompt injection before any of that context reaches the model. If your product lets people upload documents, that is not an edge case. That is a real attack path, and it should be kept in mind.
The last piece is keeping your iPhone and your Mac in sync without ever standing up a cloud server to do it. Because the moment we build a sync server, we'd quietly have recreated the exact thing we said we were avoiding. Pairing starts with a 6-digit code generated on one device and entered on the other. That code, through HKDF's SHA-26 key derivation combined with a P256 ECDH exchange, produces a shared 256-bit key, the same cryptographic standard behind Signal. And from that point on, every exchange set between these devices is encrypted with AES 256 GCM, sent over Bluetooth or local Wi-Fi. No internet required at any step. But the harder problem was not encryption. It was deciding what happens when both devices have changes at the same time. We did not want one blanket rule for every table because health data is not uniform. So the merge strategy is domain aware, table by table. User profile and preferences use last write wins. The newest update simply wins. Medications, conditions, allergies, and appointments use union merge. Both versions are kept. Nothing is silently dropped. Lab results, documents, conversations, and summaries are append only. They just accumulate. That distinction matters more than it sounds like it should. In health, oops, we overrode the older medication record is not a small bug. It's the kind of mistake that should make you stop and rethink the whole system. And the whole thing works with zero internet connection. Here's the two devices paired and syncing in airplane mode. We did not go into this hackathon planning to win anything for security. We went in trying to solve a problem we were genuinely angry about. But the architecture decisions we made for privacy turned out to be the same decisions that make a system secure. Encryption at rest, no PHI ever touching the internet, audit logging built in from the start, not bolted on afterward. And that is what won us Vanta's Best Security and Infrastructure Prize at the O1 Summit Hackathon's health track. And honestly, that result told us something. You don't have to choose between moving fast and building something that's actually secure. Because we did both in 24 hours, because the constraint came first and the engineering followed it.
So here's the hot take. Everyone tells you that you need the cloud for a health AI to be any good. We just showed you a model running on an iPhone with persistent memory, proactive calendar awareness, document understanding, and offline sync between two devices. And at no point did your data need to leave your hand. The privacy versus performance trade off in health AI is not a law of nature. It's a default that nobody's questioned yet. We are three grad students from Minnesota, and we built this in 24 hours during a hackathon. We are working towards a full test flight launch, deeper Apple Health integration, and a more complete Mac experience. If you're building in memory or in vertical AI for healthcare, do come and find us afterwards. This pattern of local inference, structured first memory, and a real boundary around anything that touches the web works for anything high stakes and not just health. Your health data should never have to be someone else's business decision. We built Sirius to prove it doesn't have to be.